Hello everyone, today we'll talk about the problem find the duplicate number. In this problem we are given an array of integers containing n plus 1 integers, where each integer is in the range 1 through n inclusive. One of them, exactly one of them, is repeated, maybe more than twice, and we have to find it and return it. It sounds quite simple. In fact, you can come up with many different types of solutions, and I encourage you, if you are not sure, to pause the video and convince yourself that this version of the task is easy. However, what we are given here has a bunch of limitations that will make solving the problem way harder. First of all, we are being told that we must solve this problem without modifying the array nums, which normally wouldn't be much of a problem, except that we are also told to only use constant extra space. On top of that, in the follow-up section, we are being asked, can you solve the problem in linear runtime complexity? So, all these limitations in combination will give us O of n time and O of 1 space complexity. So, if you want to think about how to solve this problem, or an easier version which drops some of the constraints, either not going in linear runtime complexity or using extra space, or perhaps considering the situation where this integer appears exactly twice and all the others appear exactly once, is your last chance to pause the video and think for yourself. Okay, so the key to solving this task is to look at it from a certain perspective. Let's take example 2. We have numbers 3, 1, 3, 4, and 2. And those are in an array at positions 0, 1, 2, 3, and 4. And now what we can do is you can consider the values in our array to be pointers into this very array, in the sense that the number that is in a given cell will tell us to which number of cell will have to go next. So this 3 will be connected with the red 3, so this element. This one will be connected to itself, since it's the red 1. This 3 will also be connected to the red 3. And now the number 2 will be connected to this number 3. And the number 4 will be connected to the red 4. To make it more clear, perhaps, we can rewrite it like so. Red 0 points to red 3. Red 3 points to red 4. Red 4 points to red 2. Red 2 points to red 3. And we also have red 1 pointing to itself. This type of graph is in fact called a functional graph, because what you can notice is that each vertex has an out degree of exactly 1, which means that there is a hypothetical function which, given a vertex, for instance this 3, gives us another vertex to which it is connected. What we can notice about this specific type of functional graph is that 0 has always in degree of 0. Nothing is connected to a 0 because our values here are from between 1 and n inclusive, so they do not include 0. And also that the answer to our query just so happens to be the vertex, which has an in degree of more than 1. Can you see why that is? In this problem, we are being asked to find the one repeated number in nums. And what does a repeated number mean? It means that some two values here are equal, and so their arrows point to the exact same red number. So that's exactly what we are trying to find. Now, if this sounds familiar to you, it probably should, since we have reduced this problem to finding a cycle in a linked list. In fact, finding the first vertex to be reached from 0, which lies on that cycle. Perhaps you have solved this problem already. If not, then by solving this problem, find the duplicate number, you'll also be able to solve at least 2 other problems on LeetCode for free. And for those of you who have never wondered about it, let me show you quite an ingenious algorithm, sometimes called Floyd's algorithm for finding a cycle, sometimes called the tortoise and hare algorithm. And it goes something like this. We'll start with 2 pointers, f and s, starting at 0. F stands for fast and s stands for slow. Now, as their names suggest, the pointer f in each unit of time will progress by 2 edges, and the pointer s will progress by only 1 edge. So, after the first step, the pointer s is here, pointer f is here. After another step, s is here and f is here. And after another step, s is here and f is also here. Since this happened, we can now be sure that there is a cycle, but we already knew that. And now the question is how to find the first vertex of this cycle. I will first give you the solution and then try to explain the intuition behind it. And the solution is simply this. We take our fast pointer and place it back at 0. And now both of those pointers will progress one at a time until they meet. And we can see that they meet immediately, and they meet exactly at 3. If you've never thought about it, then it would be a good idea to pause the video here and wonder a bit why. Well, first of all, why, if these pointers meet, there is a cycle, and also why the second stage will actually find the first vertex of this cycle. Here's one way to think about it. Of course, when they meet, a cycle exists. That's because the fast pointer will always be in front of the second pointer, and if there is no cycle, then it will just fall off the end of the list, and that's it. The only way for it not to fall off is for there to be a cycle, and then when at some point they are both on a cycle, then the fast pointer will be catching up to the slow pointer one step at a time. And to see why this procedure will give us the first vertex, let's first notice that the fast pointer will have traveled length e, which is the length before it reached the first vertex of the cycle, plus the whole cycle, and also plus some portion of this cycle. And this is equal to the number of steps that the slow pointer did. The slow pointer did the same e steps, and then also did the x steps, but without c, since they met at the same point, x steps along the cycle. And of course, we have to multiply this whole thing by 2, because for each step the second pointer did, the first pointer did 2 steps. And now we want s to exactly finish walking along the cycle. So the remaining steps for s are equal to the length of the cycle minus the portion already traveled, right? So we want to find this. So let's look at our equation and try to find it. Since we have e here and 2 times e here, x here, 2 times x here, so we have that c is equal to e plus x, and so c minus x is equal to e. So the remaining portion for our slow pointer to travel is exactly equal to the entry portion for our fast pointer to travel one step at a time. So indeed, this algorithm will find this very vertex. So in summary, to solve this problem, we consider the values in our array to be pointers to other cells in this array. And we find the first vertex of the cycle that is reachable starting from 0, using the standard method, like for linked list. So if you have already solved this problem for a normal linked list, the changes are quite cosmetic. And finally, you can see the solution to our problem on the left, the solutions to the two related problems I was talking about, number 141 and 142. On the right, we have the problem that just asks us if a list has a cycle. So we just run the first part of the algorithm, and if they meet, then the list has a cycle. And if not, that means we cannot push the fast pointer anymore, and so there is no cycle in the list. Now for the linked list cycle 2, we have to either return that there is no cycle, in which case we return null, or we find this first vertex in the way that I described previously. And as you can see, those portions are almost identical. And as a bonus, the two most interesting versions of this problem with some limitations dropped would be the version where the limitation of our duplicate element appearing possibly more than twice doesn't exist. So we are guaranteed that every element appears once, and then we also have another occurrence of one of these elements. This is another problem here on LeetCode. And another independent subproblem would be if we can modify the input array. We still cannot sort it, but perhaps by modifying it and not using any extra memory, it could be possible to solve this problem. And in fact, the code is quite a bit shorter than this, and it's even more magical than this, so I encourage you to find it out yourself.